Hey, we're going to walk through the first few pages of the notes about trigonometric identities. And as we go, I'm going to ask you to pause the video and do some calculations and then come back to the video and continue to work through these notes. So, in the next unit, we're going to be talking about trigonometric identities. And an identity is an equation that is true for all inputs in the domain of the equation. So normally we solve conditional equations, something like maybe we have, x plus 3 equals 7, and then we solve this and we get x equals 4. This is a conditional equation. But for an identity, that's something that will always be true. So maybe we have like x plus 5 is equal to, we could have, something like x plus 5. That's always going to be true. Okay, that's the difference between an identity versus a conditional equation. So what we're going to be talking about now is identities, true things that are true for all values that you can input into them. In this case, we're going to be talking about trig identities. So what I'd like to do now is pause the video and go ahead and enter the following expressions into your calculator and see what you get. Notice that this third expression, when we have sine of 4.5 squared plus cosine 4.5 squared, the angle here is in radians. And in order to enter it in radians, you need to put your calculator in radian mode, or alternatively, you can enter the value and then put a little r after it. And I'm going to explain how to do that. So to put your calculator in radian mode, you can simply take the touchpad and arrow up onto the thing at the top of your screen. At the top of your calculator screen, you'll see something that says degree, and then you'll see the battery. So if you take your mouse and you hover it over where it says degree and then click the pad, you'll see that it'll toggle to RAD, which is radians. That's your calculator's then in radian mode. So when you enter this equation, sine of 4.5 squared plus cosine 4.5 squared, you'll want to be in radian mode. Alternatively, if you're in degree mode, what you can do is leave your calculator in degree mode, but then when you enter 4.5, so let's say you enter 4.5 on your calculator, then you can push the pi key. And the pi key has a little arrow on it, which means that it opens up a submenu. When you push that, you'll get a pop-up on your calculator, and you'll see pi and I and R. Oh, pi and I, sorry, infinity. You'll see a little degree and a little r. This r is radians. So if you enter 4.5, then hit the pi key, and then click the R, that will put that angle as a radian. Okay, so go ahead and enter these, and then come back to the video. Okay, so I hope you tried these, and I hope that you found, when you calculated all of these, that they turned out to be 1. And from this, we're going to make a generalization, and we're going to conclude, although this isn't a proof, we're going to conclude that sine squared theta, where theta is any angle, plus cosine squared theta is equal to 1. And I'm not sure if you've seen this notation before. When we have cosine squared theta, this is really cosine theta times cosine theta, but we write it as cosine squared theta rather than cosine theta squared because it's confusing. This latter notation is confusing because we don't know what squared. Is theta squared or is the whole ratio squared? So to be safe, we write cosine and then the little 2 theta. That means the whole function is squared. Okay, and this particular identity is called a Pythagorean identity. And the reason it's called a Pythagorean identity is it comes from the Pythagorean theorem. And I'm going to show you why it makes sense right now. So if we think about the unit circle and what we know about that, because we spent a fair amount of time studying it, I'm going to draw a unit circle. And the value of the unit circle was, if we knew an ordered pair on the unit circle, let's say its coordinate is x, y, then we knew the sine and cosine values for that given angle, right? So if I call this angle here theta, I can use Pythagorean theorem. So initially I'm going to use Pythagorean theorem with my little right triangle that I just drew. And on the unit circle, the hypotenuse is 1. So normally the Pythagorean theorem is a squared plus b squared equals c squared. C is the hypotenuse. On a unit circle, the hypotenuse is 1. And the legs of the triangle we can write as x squared plus y squared. That's simply the Pythagorean theorem. But now we want to go ahead and put in what x and y are. So on the unit circle, we know that x is equal to cosine theta and y is equal to sine theta. So this is on the unit circle. And now we can substitute those values in for x and y. So we can say that x is equal to cosine theta. So now we have cosine theta. So I'm going to write cosine squared theta. Plus y is sine theta, so sine squared theta is equal to 1 squared is 1, and this is our first Pythagorean identity. Okay, we're going to flip to the next page now, and we're going to explore some other identities. So you should go ahead and, now and enter these trigonometric expressions into your calculator to evaluate them. These are all in degrees. All the angles are in degrees, so you don't have to worry about radians here. But go ahead and calculate all of these values and then come back to the video. Okay, I hope you got the same values that I found. I have entered them now. And I want to talk about what's happening in these cases using the unit circle. So let's take a look at the first angle where we have cosine 25 degrees and cosine of negative 25 degrees. So I'm going to draw a unit circle and I'm going to sketch the two angles. So I'm going to sketch 25 degrees and I'm also going to sketch negative 25 degrees. And then remember, on the unit circle, the cosine is the x value. So let's say this point has a coordinate AB. That means that the point where that coincides with negative 25 degrees by symmetry will have the coordinate A negative B. So if we compare these two angles, we can see that we have the same x values for both points, right? We have A and A, so that means cosine of 25 equals cosine of negative 25. And we can do a similar analysis for all of these other angles. So let me draw the next angle. So if I sketch 220 degrees, so I would go 180 degrees plus another 40. So this is 220 degrees. And then I'm going to sketch negative 220 degrees, which means I start at the positive x-axis and I rotate in the other direction. So this is negative 220 degrees. And once again, let's look at the coordinates on the unit circle. If I say this is the point AB, that corresponds with negative 220, so then the point that corresponds with positive 220 would be A negative B. And once again, we can see that we have the same x value, so the same cosine. I'll do the last two a little more quickly. So I'm going to go ahead and sketch both angles. So I'm going to sketch 172 degrees, and then I'm going to sketch negative 172 degrees. And once again, we can see that we would have the same x values. And I will do the last one. I'll sketch 325 degrees. So that's going to be in the fourth quadrant. So something like this. And then I will sketch negative 325 degrees. So I'm going to go in the opposite direction. So it'll be something like that. This is 325 degrees. And once again, we'll see that we have the same x coordinate in each case. So if this is AB, this will be A and negative B. Okay, so what's our conclusion? Our conclusion from these is that cosine of theta is equal to cosine of negative theta. And this is called one of the even identities, and there are a number of those. And we did the justification using the unit circle, but if we want to write it out, why does this make sense? I would say that the points on the unit circle that correspond with theta and negative theta, whatever angles they are, have the same x coordinate, which means they have the same cosine value. So we can conclude, so cosine of theta is equal to cosine of negative theta. All right, now we're going to go on to the next exploration. And I encourage you to stop the video and to punch these values into your calculator. Notice that these angles, so when we have negative pi over 8, pi over 8, pi over 3, and negative pi over 3, these are in radians. So you'll have to put your calculator in radian mode in order to get the appropriate value. So pause the video, do the computations, and then come back. Okay, just like the previous example, I'm going to try to figure out what's going on by making some sketches on the unit circle. So I'm going to draw the unit circle, and I'm going to sketch these two angles. So I'm going to sketch negative pi over 8 and pi over 8. Remember, pi over 4 is 45 degrees, so this will be half of that. So let's say this is pi over 8, and then I'm also going to sketch angle negative pi over 8. And then we're going to think about the values on the unit circle. So by symmetry, if the point that corresponds with pi over 8 is A comma B, then the one that corresponds with negative pi over 8 will be A comma negative B. And we can see that that's the reason that we have negative sine pi over 8, because these values, the y values, are opposites. Let's do the next one. So let's see what that looks like on the unit circle. So pi over 3, remember that's the same as 60 degrees. So I'm going to go ahead and sketch these two angles. So I'm going to sketch pi over 3. And then I will also sketch negative pi over 3. And then if we look at the coordinates of these points on the unit circle, let's say this is AB. This point down here will be A negative B. I'm not going to sketch the other two. The argument is similar. So we can go ahead, we can make a conclusion here that sine of theta is going to be the opposite of sine of negative theta. That's a conclusion. That's what we're seeing, right? Because here, in this case, we have sine of theta is the opposite of sine of negative theta. And that's the case for all of these angles. Be true for any angle because it's an identity. And this is called an odd identity. So the previous one with cosine was an even identity, and this is called an odd identity. Okay, so why does this make sense? So we've shown the justification with the unit circle. I'll write it out in words. The reason it makes sense is the points on the unit circle that correspond with theta and negative theta have opposite y-coordinates. So we can conclude that sine of theta is equal to negative sine of negative theta. Okay, I'd like you to go ahead and do these calculations on your calculator. And once you do that, come back to the video And remember that pi over 6 and pi over 3 are in radians. So you will have to put your calculator in radian mode or use the little r in degree mode to make your calculator know that the angle's in radians. Okay, I hope you found that each pair of values have the same trig ratio. So sine of 50 is the same as cosine of 40. And sine of pi over 3 is the same as cosine pi over 6. Sine of 11 is the same as cosine of 79. So we need to figure out what's true about these angles. So if you think about it, or stop the video, think a little bit, and see what you notice about these angles, and then come back. So the conclusion here is that these are complementary angles, right? So that means they add to 90 degrees if we're in degrees, or pi over 2 in radians. So, for example, 40 degrees plus 50 degrees is 90 degrees. 11 degrees plus 79 degrees is 90 degrees. Pi over 3 plus pi over 6 would be 2 pi over 6 plus pi over 6, which would be 3 pi over 6, which is pi over 2. So in each case, we have complementary angles, and we can make a conclusion. So in this case, we have, let's say, theta is 50 degrees. Then 90 minus theta would be 40 degrees. So really what we have is sine of an angle is equal to cosine of the complementary angle. So I'm going to write a few versions of this identity. So the first one, we have sine of theta is equal to cosine of 90 degrees minus theta. If we look at the same identity in terms of radians, that would be the second one here, we could write that sine of theta is equal to cosine of pi over 2 minus theta. So this is if we are in radians. And the second one is in degrees. We can also write them the reversed way. So we can write cosine theta in terms of sine theta. So we can also write this equivalently. We could write in terms of radians, cosine theta is equal to sine of pi over 2 minus theta. And we could also write cosine theta is equal to sine of 90 degrees minus theta. These are called cofunction identities, and it's called cofunctions. This comes from, the comes from complementary, because it has to do with complementary angles. I'm going to explain why this makes sense. I'm not going to use the unit circle here. I think it's a little easier just to use a right triangle for this explanation. So let me explain why this makes sense. So let's go back to when we did right triangle trig with SOHCAHTOA. So I'm going to go ahead and draw a right triangle. I'll label the vertices A, B, and C, and I'll label the side lengths a, little and little c. So by SOHCAHTOA with right triangle trig, let's say I'm going to label angle A. I'm going to call that theta. We can find the measure of angle B, right? So if I want to find the measure of B, it would be 180 minus 90 minus theta, or 90 minus theta. So this angle is 90 degrees minus theta, or in radians, 90 degrees is pi over 2 radians. So pi over 2 minus theta, that's equivalent. Okay, so let's use SOHCAHTOA. I want to write the sine of A, okay? So sine of A, if I'm looking at angle A, this side will be my opposite. That would be a hypotenuse. That would be adjacent relative to angle A. So sine of A is opposite over hypotenuse, which is A over little c. Let's try the same thing, but I want to write the cosine of B. Okay, so thinking about my triangle in terms of B, this side is the opposite, and A now becomes the adjacent. So cosine of B is the length of the adjacent side, which is A, over the length of the hypotenuse, which is C. Okay, so we can see that sine of A is equal to cosine B. And this is true in any right triangle, and we also know that B is 90 minus theta. So this is the same thing as 90 minus A. So let's say this is 90 minus A. Same thing. So we can conclude that instead of A, I'm going to write theta though. So I'm going to write sine of theta is equal to cosine of 90 degrees minus theta, which is the same thing as the cosine of pi over 2 radians minus theta. So that's a justification for one of these cofunction identities. In example 5, we're going to confirm some other identities. So to do that, we're going to think about the unit circle again. So I'm going to just review the unit circle. I'm going to draw my unit circle. I'm going to pick a point on my unit circle. I'll draw in a little right triangle, label the sides, the lengths X and Y. And we've done this before. We know that sine of theta is the Y coordinate, cosine theta is the X coordinate, tangent theta is Y over X. And last year you should have learned these reciprocal functions. So cosecant of theta is the reciprocal of sine. So sine is opposite over hypotenuse. So cosecant of the theta is hypotenuse over opposite. Hypotenuse, this is theta. Hypotenuse is 1 on the unit circle, and the opposite side is y. So cosecant theta is 1 over y. Secant theta is hypotenuse over adjacent. It's the reciprocal of cosine. So that's going to be 1 over the adjacent side is x. And cotangent theta is the reciprocal of tangent, so it's x over y. Okay, so we're just using the definition of the trig ratios in terms of right triangles, so opposite over hypotenuse, etc. Okay, so once we know that, now we can write some new trig identities. So tangent theta, when we were working before, we said it was y over x for the unit circle, but instead of y and x, we can use the other trig ratios. So instead of y, we can write sine theta, and instead of x, we can write cosine theta. And that is a new trig identity. The same thing with cotangent theta. So we have x over y, but x is going to be cosine theta over sine theta. And these two identities are called quotient identities because we have one trig function divided by another.